Welcome back to another episode of the Physics Prior. In this series, we are discussing science in general and trying to define it, determine what makes science science. And in this particular episode, we're going to be talking about scientific methods. Now, note that the S is important. Scientific methods in the plural. It's methods, plural, because there is no one scientific method. As it says there, scientific methods refer to the principles and procedures for the systematic pursuit of knowledge involving the recognition, formulation of, you can read that yourself. Right, the basic idea is this. Scientists go about their process of discovery normally pretty methodically. They follow a certain routine, a certain process that gets them from point A, which is a kind of a question, a wondering, to point C, a reasonable conclusion, by following this regular systematic process, by following the same sort of steps each time. But the steps can actually change, and the path from point A to point C is not exactly always the same. Generally speaking, scientists want to know something. They've recognized a problem, they've come up with some sort of question, and they've phrased that problem as specifically and exactly as they can. And then they go about to collect data. They go about doing some experiments and observing things in order to gain some more information on the problem or question that they've come up with. And finally, they come up with these predictions, these hypotheses, which they can then go about testing in the lab in some controlled condition. The common steps for the scientific method are as follows. But please remember that these common steps are not necessarily always followed in exactly the same fashion. But the common steps are: you recognize a question, puzzle, unexplained fact, make a hypothesis or an educated, good guess to resolve the puzzle, predict some consequences of the hypothesis, perform experiments or make calculations that test those predictions, and finally, the end result is that you come up with the simplest general rule that organizes the three main steps. In other words, some general rule that explains the question or puzzle that you came up with. I am hoping that you are fairly familiar with the scientific method, or with these common steps to the scientific methods at this point in your education. Much more important, I think, is what Paul Hewitt calls the scientific attitude, and I think it's also important for the classroom. The scientific attitude, as he says, is one of inquiry, experimentation, and most importantly, willingness to admit error. If you'll come with me as I go across the classroom, I will talk about in particular that last point there, the willingness to admit error. And I hope you can see this quote here. This is a favorite quote of mine, and it really sums up the scientific attitude. It's from Niels Bohr. And Niels Bohr said that an expert is a man who has made all the mistakes which can be made in a narrow field. In other words, making mistakes, especially in science, is part of the process. It's good. Scientists, and I really love this, scientists are experts at changing their minds. See, that may be an idea of science that's completely foreign to you, but scientists change their minds all the time. Because when new data comes up and contradicts an old hypothesis, out goes the old hypothesis. They have to change their minds. That's the nature of science. You have to accept the results of an experiment. Richard Feynman actually has a really great quote on this.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess to see if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience, compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
If it disagrees with experiment, it's wrong. Now, Richard Feynman said that. Richard Feynman was a brilliant physicist and a great teacher. But if Richard Feynman made a prediction, and that prediction was contradicted in the laboratory, doesn't matter how smart or how great or how famous he is, if it disagrees with the experiment, as he says, it's wrong. It's in light of this attitude that scientists have a different definition of fact than we do in everyday language. When we think of facts in day-to-day language, we think of something fixed in stone, unchanging. But for scientists, fact means something different. The closest scientists get to fact is close agreement, when a group of people more or less agrees with each other fairly closely about something. Now, those people who agree have to be competent in their field. That means they have to be good at what they do, but they never get to that fixed in stone. All they get is pretty close agreement about something. The definition of hypothesis also takes on a particular shade of meaning given the scientific attitude. It's not only that it's a guess and that it has to be supported by experiment. Let's move to this check question. Which of these is a scientific hypothesis? Pause the video, take a look now, and determine your answer. It turns out that even though they all are fairly ridiculous hypotheses, they are all still scientific hypotheses. A scientific hypothesis must have a test for proving not rightness, but wrongness. In other words, it's only scientific if you can prove it wrong. And each of these statements can be proved wrong by a simple test or experiment. In light of that definition of hypothesis, which of these is not scientific? We have protons, undetectable particles, charged particles, or we can say that all of the above are scientific hypotheses. Pause the video and determine your answer. In this case, it is the second sentence. Undetectable particles are some of nature's secrets. That is not scientific. And it is not scientific because it cannot be disproved. They say there it has no test for wrongness, so it is not a scientific hypothesis. It has to be disprovable. It has to be able to be contradicted in order to be scientific. Can you prove it wrong? That is the question that you should ask when you are determining whether or not a hypothesis is scientific. Laws and theories are as solid as science gets, because a law is a hypothesis that has undergone repeated testing and has not been contradicted, and a theory is almost like a body of several laws that are all related to each other, and it's been very well tested and supported by experimental results. So if you want to get to solid fact, if you will, or solid ground, the most solid ground you can stand on in science is theory. But even theory, well, I'll let you answer the question. Which do you think can also change over time with further study? I'm cheating the answer. The answer is that both facts and theories can change over time with further study, because theories are based on facts, and if facts can change over time, then so can theories. But one last question for you. A person who says that's only a theory likely doesn't know that a scientific theory is a guess, number of facts, hypothesis of sorts, vast synthesis of well-tested hypotheses and facts. Pause the video to determine your answer. And the answer is D, vast synthesis of well-tested hypotheses and facts. Theories are pretty solid. theories are more than just a list of facts. Theories are a body of related knowledge, a body of facts, a body of hypotheses that have been very well tested and confirmed in the laboratory. The word synthesis means that they're all related to each other and organized according to one single organizing principle. They're pretty solid, but even theories can change. That's it for this series. Thanks for watching The Physics Friar.